So today we're going to just extend what we learned last day about this idea of substituting to help us find an integral. And the first thing that we're going to look at is maybe a way that we could possibly speed up what we did yesterday. So the power rule, if we were to do the power rule for integrals, the general one, you just see if I can get some better resolution here on the screen. Still not that great here, just one more try. Okay, well that's a little better. So if you see that you have a function, and that function is raised to a certain exponent, and you also have the derivative of that function, then that's the chain rule. We can do that going the power rule backwards. So in this sense, if I had n was my exponent, I'm going to go one higher, so to n plus 1, and then divide by n plus 1. So we can work the power rule for integration on any function if it's nice enough that we see it there. Now obviously it's an ideal world when this happens, but it's not to say it won't. I mean, it can speed things up. So for example, I'll do the first one with you. If we were to take a look at these two, can you see one that's a function and one that's the derivative? Yeah, so this is the function here, and this is the derivative here. So if you recognize that pattern, the next thing, as I said, is we're doing the power rule for integration, so we need to know what power are we doing. Well, there's a 1 here, so to go from 1, the next one higher is going to be the function e to the x plus x, 1 higher divided by that number plus a constant. So if you see the pattern, it's obviously a lot quicker than going to the trouble of substitution. Okay? So what I'm going to have you do then is try to work out, do you recognize the pattern and can you apply it? I will just let you know that not all of these questions does the pattern apply. So first you should ask yourself, can I do this with the simple form that we just talked about, or do I have to go back to making a substitution like we did last day? All right, it looks like people are madly working away, so I'm hoping that's some good news. Just to get more space, I'll move it back over in a second. So do we recognize a function and a derivative here? Just hands up if you do, so I get an idea. Okay, good. So the exponent is the tricky one here. Here's my function. Here's my derivative. And the exponent is a half this time. So that means I'm going to take the function, x cubed minus 2, 1 higher, divided by 1 higher. So that's going to be 2 times x cubed minus 2 to the 3/2 all over 3 plus a constant. All right. So this next one, does it work for this next one? Is the function and its derivative present? Yeah, I think so. If I pick this as my function, 1 minus 2x squared, then this piece up here, that would be my derivative. So what's the exponent? Good. Be careful. This time the exponent is -2. Okay, so if I rewrite this, it's going to be my function 1 higher. So that'll be 1 minus 2x squared. 1 higher would be -1 divided by -1. So most likely we would write this as -1 over 1 minus 2x squared plus a constant. Now, even though we're trying to build up a little bit more familiarity and get faster at it, do some shortcutting, it's not to say that if you didn't get the shortcut, you couldn't go back to substitution. Substitution works here. It's just sometimes it takes longer than doing, you recognize it, you can just go for it. How about the next example? Is the next example ready to go? Are we able to do a shortcut to it? How about this? How about I say you can do a shortcut, but what's my hesitation? Okay? Say it one more time.
Make it into a point with these four shortcuts.
I just because there's some construction that's sort of sorry, Jeff.
Like make it into one with these four shortcuts. Like add the stuff we did yesterday.
Oh, okay, yeah. The stuff that we did yesterday, that's what we have to add into this. So if we looked at the two pieces, it might be easier for people who aren't seeing it at the moment. Here's a monster hint. If I'm faced with the choice of those two pieces, cos squared and sine x, cos squared does not produce the derivative sine x, so that's not the good match. But if I looked at it this way, and I just looked at the inside, that could be my function, and that could be my derivative. But what's missing from the derivative? That negative sign. So I'm going to put a negative on the outside and a negative on the inside to balance it out. Now I can use this shortcut. So that wasn't too bad. I just had to add the negative sign in. Some of your exercises yesterday, once you added in that constant, the multiplication, you could use the power rule now like we've been doing as a shortcut. So the function and the exponent is 2. So there's a negative out front. It's going to become cosine x cubed over 3 plus a constant. All right. So I'll let you take a look at the next two. And then we'll discuss them in just a second. All right, so what do we think about the first one? Does the pattern apply? It does. Okay, explain it. What do we have to add?
2 and then a half.
Okay, so we're going to have a 2 and a half. Then let's take a look at it. So you want to put a 2 there and a half there. Okay. Yeah, that looks like you're setting it up properly, but does the general power rule apply here? The one we've been using for the last 4 examples? Well, in this situation it doesn't, because we would need the derivative of sine x squared. We don't have a cosine anywhere in there, so we have to go back to the substitution like we did last day. So you're on the right track about putting in the half and the 2, but this is the piece that I'm using as my function. So I'll say let u be equal to x squared, then du is 2x dx, and I'll assume that's why we put the 2 up here. So we can go ahead like we did last day. That's going to now be equal to 1/2 the integral of sine u du. So who has a derivative of sine? Yeah, negative cos. So this is going to be 1/2. Sorry, negative 1/2. Plus a constant, and for us, u is x squared, so we replace that to look like this. Okay. So it's not that we couldn't do it; it's just the shortcut failed. So the second one, what do we think? Will the shortcut work for the second one or no? Shaking your head. How come? There's no other e to the something, right? So we don't have a power rule, but we can still do this by substitution. Just for the sake of clarity, I'm going to do it in a nice big slide so I don't have to jam it in there. So this is going to be the integral of x plus 1 e to the x squared plus 2x. So you might be able to look at that and notice where the function and the derivative is. How many people, hands up if you can see a connection right now? It's a little tougher to find it in this one. Okay, not bad. So the connection is between this as my function and this is my kind of derivative. So I'll walk you through this is sort of how I would end up with two pieces. This would be e to the x squared plus 2x dx. And the reason I put that 2 there is now when I rewrite the integral, I have 2x plus 2 e to the x squared plus 2x dx. So now I can see, here's my function, and that's the derivative to match it. So a half was needed to correct that. So u is going to be equal to x squared plus 2x. The differential for u is 2x plus 2. So now I can replace those pieces, and I would have 1/2 the integral e to the u du. So 1/2 e to the u plus a constant. So 1/2 e to the x squared plus 2x and a constant. So I'll just pause it while you're copying that. Okay, so let's go back. Yeah. What can you do, right? Construction is construction. But the last thing today, I mean, so far, okay, so I have to talk really fast in between the breaks of the jackhammering. But one thing, so far we've talked about substitution as a way to recognize the function and its derivative. Now we're going to talk about substitution as a strategy. So for example, this first one with the square root, if in your head you're thinking, well, I can probably do this without using substitution, I'd agree. But it's going to be tougher to do this right from here to finding your answer. So what you might say to yourself is, well, it'd be a lot nicer if I was dealing with just the integral of x dx. That's what would be a lot better for me. So because that would be easier, let's make a substitution. We'll get rid of the 2x minus 1, and that means my differential this time is going to be 2 dx's. Okay? So the integral would be the integral of root u dx. And I have to get rid of that dx, right? It needs to be in terms of u for this integral to work. So I can do that fairly easily. That means, according to this, right here, dx is equal to du over 2, right? 1/2 du. So that's what I'm going to do for my replacement. I'm going to call this root u and 1/2 du. Okay. So that integral is actually going to be easier for us to work out. This will be 1/2 the integral root u du. So that's 1/2 u to the 3/2 over 3/2 plus a constant. And that gives me, let's see here, 3 u to the 3/2 over, sorry, no, shouldn't be a 3 there. It should just be u, and I've got the 3 on the bottom. Okay. And of course, we always want to go back to where we started. It's not going to be funny very soon. It's going to start to get annoying. So back to where we started, which is in terms of x. So it would be that if we did it in terms of x. So again, the strategy this time was to try to make the integral easier. It wasn't because we saw the function and its derivative. It's just maybe we can make the integral easier to work with. So anyways, the last thing we're going to try is, again, this idea that substitution can help make the integral easier. You'll get used to kind of what situations help out more. So here's another situation where substitution definitely makes this integral easier to work with. If you try to pair these up, you might say, okay, well, there's my function, but that's nothing at all like the derivative. There's this extra stuff there. I can't really match it up. This is quite a challenging antiderivative without a better technique. So what I'm going to show you is what your thoughts, to give you some idea of how you might predict your substitution. So if I was to look at this integral, it'd be really nice if instead of that, I would rather have it be something like this, because it's okay for stuff in the brackets to be messy, because it'll just be a power rule. But stuff under the square root, that's harder to work with because of that square root. So what I'm going to do is make a substitution that removes all these extra pieces inside of the square root. And then you'll kind of see, if you follow along with me, what happens to the rest of the integral. Okay, so let's try that. We're going to substitute to get rid of what's underneath the square root sign. If I do, then the differential for u is 2 dx's. And from that I could say dx is 1/2 du. So let's make a substitution here like we would have before. This will be now the integral of x root u times 1/2 du. Okay, so I'll tidy this up a little bit. I'll move the half outside the integral. And as simple as it might look, you should probably all be saying, well, that didn't help if you have two variables still, right? But this variable that I'd like to get rid of, x, I can get rid of it because I have this relationship up here between u and x. So what would x be equal to if I solved? It would be equal to u plus 1 over 2. So that's how I get rid of that piece I'm not looking for. So u plus 1 over 2. And I'll get rid of that half on the bottom. I'll move that outside. And this is actually what I end up with, which is going to be a lot better to work with. Because all I have to do now is I can expand this and use the power rule. So if I expanded it, I'd have 1/4. 1/2, that'll be u to the 3/2. And then 1 times root u will be u to the 1/2. Okay. So it's possible to find this. It's much easier than had we have started where we did, because this antiderivative right here is just the power rule. So it'll be 1/4 u to the 5/2 over 5/2 plus u to the 3/2 over 3/2. And of course there's a constant. So what I could do to finally tidy this up, this would be 1/4 2/5 u to the 5/2 plus 2/3 u to the 3/2. And I want to put it back in terms of x. So I'll replace the u's. Maybe I'll put that 1/4 in there too while I'm at it. So if I put 1/4 into each of these pieces, then I'm going to end up with, let's see here, 2 over, what is that, 2 over 10? So 1 out of 5, no, 1 over 10, thank you. It would come to me, I know. But 2x minus 1 to the 5/2 over 10. And then the next one is going to be 12, so 1/6. So that looks like where I should end up. And again, if you look at where I've ended up compared to the integral I started with, it's really hard to see how would this derivative here get me back to that, the derivative of this function, how would it get me back to where I started? A lot of simplifying, factoring, common denominators would have happened to get there. But again, not obvious, but substitution can help us find what the antiderivative was when the situation's difficult. So I've run out of space. I'll have to do the next one on another slide, but I'd like you to give it a shot on your own. I'm just going to put it up here. Let's talk strategy. If we were to make a substitution what do you think would be the appropriate thing to shrink? Instead of having, well, I mean, our choices would be x plus 4 or 2x plus 1. What do you think would be, the best thing to shrink down? X plus 4 is correct. Can anybody think ahead as to why x plus 4 would be the better thing to substitute? Well, the square root's part of the problem. It's easier to find. Yeah, that'll be true too, because the things will work out nicer with just x instead of 2x. But yeah. Du equals dx, yeah. Really, what's going to end up happening is we're going to get a monomial on the denominator, which makes it easy too to use power rule, because we can split this up into multiple pieces. So anyway, give it a shot. That is the one that we would want to shoot for here, is substituting for x plus 4, and then we'll see how it turns out. Okay, so I'm going to try to catch up to you. I'll put another slide up just to make the room easier to see. Can somebody just double check that I've written it properly before I start? Is that the correct question? Okay. So the strategy we said was we're going to make this piece into a single, so that way we can break things up. So du is going to be equal to dx. So that means this time I start with those substitutions and I still have an x. But I can use this equation here to say that x equals u minus 4. And I'm going to take that and put it into here. So now I'll get 2 u minus 4 plus 1 over root u du. So what I'll end up with is 2u minus 7 over root u du. That's a little easier to work with. Don't they know we're trying to learn here? Holy smokes. Okay, anyway. I'll be curious to know how badly that shows up on YouTube, actually. See how good our microphone is if it's catching the jackhammers. Yeah, so that's part of your homework tonight, is to go home and listen to this and tell me if the jackhammering shows up. Yes? So in pieces, what this would look like is the integral of 2u over root u minus 7 over root u. So I can use my exponent laws, and I'll get 2u to the 1/2 minus 7u to the negative 1/2. And now I'm ready to go with the power rule. So this will be 2u to the 3/2 over 3/2. And I'm going to take away 7u to the 1/2 divided by 1/2. So this will become 4/3 u to the 3/2 minus 14u to the 1/2 plus a constant. Yeah, you're just expecting me to freak out at one of them? They're just doing their job. They're just doing their job. So 4/3 u to the 3/2 minus, see this, the construction's got me, if I make any mistakes today, it's their fault. I have to make my substitution back in there, which was x plus 4. So this is going to be x plus 4 to the 3/2 minus 14 x plus 4 to the 1/2 plus a constant.